The first semiconductor that we're going to look at is a part called a diode. And those things that I've given you are diodes. The schematic symbol for the diode looks like this. Now, on the schematic diagram, you will actually see this filled in solid black. I won't do it on the board because it's a big hassle with the whiteboard and the marker, but it's actually filled in solid black. It's got this bar at this end like this. The diode comes from the Greek word, the name diode comes from the Greek word di, meaning two, and ode, like electrode, two leads. Two leads. A diode is simply a semiconductor that has two leads. And we have names for these two leads. The lead on the left is called the anode, A-N-O-D-E. And the lead on the right is called the cathode, C-A-T-H-O-D-E, cathode, the anode and the cathode. If you need a way to remember which lead is which, you can remember it the way my good buddy Nathan Bush from Dallas, Texas remembers it. He's got a girlfriend named Kathy, but she's kind of a wino, and you can always find her at the bar. So the cathode is the bar end. Kathy at the bar, get it? Cathode bar, anyway. And if you look at the diode that I gave you, diodes that I gave you, you'll see a ring or a stripe on one end. Obviously, that's the cathode end. And the other end's the anode. The reason that it's important to know which lead is which is that the diode is a one-way gate for electric current. According to the schematic diagram and according to the way we think of electric current flowing, conventional current from positive to negative, electric current only flows through the diode if it's going the same direction the arrow points, which makes a lot of sense. The current will only go through the diode in that direction. It won't go back again. It won't go back the other way. It only goes through one direction. Let me put this diode in a demonstration circuit for you and show you how it works. This is just a demonstration circuit that shows you how the diode works. This does not have any function whatsoever. This doesn't do anything. But let's go back to the schematic diagram that we've seen several times already with the battery and the lamp like this. And there's our complete circuit. Everybody with me so far? We went through this before. I'm going to break the circuit right here. And I'm going to put a diode in series with the battery and the lamp. Remember, in a series circuit, anytime the electric current has to go through one part to get to another part, they are in series. All right, well, if I connect this circuit now, do you suppose this lamp should be on, will be on or off? Should definitely be on, sure. Okay, so let's connect this guy up here. And I have the red wires connected to the positive side of the battery, and it goes from there to the diode. Which side will it connect to, the anode or the cathode? Anode. Anode end, right? And I'll use this really bitchin' yellow wire here, amarillo, to connect to the cathode, and then the other end of the cathode goes to the lamp, and if we're correct, this should light up. Ooh, ah, all right, so it's lighting up. If I reverse the diode, it should not light up. So I'm just going to disconnect the diode here and just turn it around. If the diode's good, ooh, not so impressive when it doesn't light up. All right? And, of course, now, what we had first when it was conducting is, of course, service call, radiation leak, Sector 5, all blue personnel to the shelters immediately. All right, so when it was running, of course, the current was going this way. Is it going the same direction as the arrow? Yes, it is. It's conducting. Then I reverse the diode. When I turn the diode around like this, Remember, the current still wants to go from positive to negative. We haven't changed that. But the diode's like this. It's going, hey, no way, Jack. You're not going through me. Forget it. And it's blocking it. Now, without touching the diode at all, how do you suppose I could change this circuit around to make the light bulb light up?
Change the battery.
Get a new battery?
Reverse
the connections on the battery. Sure. If I reverse the connections of the battery, that's going to change the direction the current flows naturally. Ooh, okay, really good. There you go. It's magic. Magical. Okay, so, and now, of course, the schematic diagram looks like this. We've turned the battery around. That's the negative now. There's the positive side. Now current goes this direction. Now this is the source path, isn't it? We turn the battery around. Return path. Hey, go in the same direction. Shit, it's on. It's going the same direction. It's on, period. So you'll notice, too, that it didn't matter whether I put the diode in the source path or the return path. As long as it's going the right way, it'll conduct. Now, again, this is just a demonstration circuit. This is just to show you how the diode works. But one of the places we use a diode a lot is to change alternating current into direct current. Remember that alternating current sometimes goes this direction, then it goes this direction. It's constantly changing direction. One direction, then the other. Well, we take that AC and we run it through the diode, and here's what happens. The diode lets it go one way, but keeps it from going back. It can't go back. The diode allows it to go one direction, but it can't go back through the diode. Is it working? Yeah, it's working. Okay, it can't go back. Everybody's watching the camera. It can't go back. It keeps the current going in just one direction, and that's the definition of DC, isn't it? Remember I said current that just goes in one direction is DC. So we use diodes to change AC into DC. Turn in your blue book to page R5. The process of changing alternating current into direct current is called rectification. The process of changing AC into DC has a name. It's called rectification. Another really horribly big term. What does that mean? Well, it comes from the English word rectify. Rectify, of course, means to make something better. You got a problem, you rectify the situation. Well, our problem is AC. AC is really good for some things. It's great for motors and toasters and weed whackers and hair dryers and stuff like that. But alternating current is no good at all for electronic things. Things like computers, televisions, VCRs, radios, they all require direct current. So we rectify the problem of AC by running it through this diode and changing it into DC, a process we call rectification. We're rectifying the problem of AC being so cruddy, we turn it into DC. And in fact, a diode that's used to change AC to DC, as you see here on page R5, is called a rectifier. A diode that changes AC into DC is called a rectifier. And you see that this page, it doesn't say diodes on it. It says general purpose rectifiers. All rectifiers are diodes. All rectifiers are diodes. Now, we do have places where we use diodes not as rectifiers. Not all diodes are used as rectifiers. That is, not all diodes change AC into DC. For instance, in a pinball machine, you know that there's diodes across the flipper coils of a pinball. Those ain't changing AC into DC. Those are doing something else. I'll tell you on Saturday what those are doing. But for the most part, diodes are used to change AC into DC. And in fact, it's a real common problem on these switching regulator power supplies. Much of the time, the only thing that's wrong, and we'll do this on Wednesday, much of the time, the only thing that's wrong with your power supply is one 25-cent diode. It's very common. The last class I did, virtually half the problems were just one single diode. You'll see how simple this really is to fix. Everybody cool so far? Now, before we get into testing the diode, I really need to show you a little bit more about what's inside the diode. Inside the diode itself is made of something called silicon. Silicon Valley, here's where we are in Silicon Valley. Silicon, pure silicon is obviously one of the elements. Basically, silicon is dirt, it's sand. Pure silicon by itself is actually an insulator. Something that does not conduct electricity very well at all. It doesn't conduct electricity at all. Pure silicon is actually an insulator. The diode starts out as a single chip of silicon. A single little chip of silicon. But if it was made out of pure silicon, it would never conduct electricity at all. So they add some chemical impurities to the diode. You don't have to know this, they're called dopants. What it does is it changes the atomic structure of the silicon. They divide it into two halves. By adding these impurities as they make the diode, one side ends up with extra electrons. Remember, electrons have negative charges, don't they? If I have something that has extra electrons, that thing now has a negative charge. In fact, this silicon is known as type N silicon, N for negative, obviously. The other half of the little chip of silicon has electrons taken away from it. Pretty weird deal. Through a chemical process, they actually strip some of the electrons out. By taking some of the negatively charged electrons away from one side, it turns it into a positively charged piece of silicon. I mean, naturally, if you have something that has the same number of positive and negative charges, and then you remove some of the negative charges, what's left is more positive than negative. And we call this type P silicon. P for positive. So we have this silicon chip that's made out of type P silicon and type N silicon. Now really, in your little diode, it really looks like this. It's a little wafer, a little disc. And it's divided in half like this, with type P on one side and type N on the other. Here's the component leads attached to the silicon, and then they cover the whole thing with epoxy plastic. That's what your thing looks like inside. In fact, if you see one of these broken in half, as you will probably see eventually in your life, you can actually see the little chip of silicon inside. Or if you take a pair of dikes right now and just slice your diode in half, you'll see that it'll break right at the silicon. Anyway, so we have this diode here, and it's type P and type N. Well, remember I mentioned to you before that opposite charges attract. Just like opposite poles of a magnet attract. If I put North Pole next to South Pole, they attract each other. Well, over here we've got positive charges here and negative charges there. Gosh, why don't they just kind of, come together and neutralize each other? They're opposite polarities. Well, here's why not, and this is important. If you've been asleep until now, wake up. Because right here, where the type N and the type P, or the type P and the type N silicon meet, we have a really important thing that you just got to know about, and it's something called the PN junction. The PN junction acts like a barrier and keeps the type P separate from the type N. It's kind of like a little brick wall in there, although it isn't really anything at all. It's like a little barrier that keeps the type P separate from the type N. Now, I think what really happens in this area, and I'm not a physicist by any means. Like I said, I'm a high school graduate, and that's all. But I think a little bit of the electrons and the positive charges kind of do mix together a little bit and form a kind of a neutral, like a little Switzerland in there in between France and Germany, kind of. But the important thing is to know that the PN junction exists. That is, it's a barrier that keeps the P separate from the N. The reason it's important is that when we test diodes, and as you'll see later on when we test transistors and even integrated circuits, what we're going to do is test this PN junction and see if it is working properly or not. Now, of course, I'm going to tell you how to do that in just a few minutes. But this PN junction is real important. It's where the type P silicon meets the type N silicon. Let's put this diode in our demonstration circuit and see how it works. Whether or not you understand how it works is not terribly important. I think it's fascinating how this thing works, and I'm going to explain it to you. If how it works doesn't make sense to you, that's okie dokie, because I'm going to show you how to test it in just a second. But right now the diode is facing this direction. So I'm going to put it in the circuit that we had before, with the battery, the diode, the lamp, and according to y'all, this should be on right now. So here it is. There's the battery. There's the lamp. Is everybody with me so far? This is pretty simple. And it should be on now. Well, let's see what happens. Remember that similar charges repel each other. Again, just like with magnets, if I try to put two south poles together, they'll repel each other. And it's the same thing here. Here I have the positive charges in the type P silicon. These have a nickname, by the way. These positive charges are called holes. They're called holes because essentially it's like an atom with a hole in the electron shell waiting for an electron to fall into it, basically. So they're given the nickname holes. These holes can move around inside the silicon crystal. So can the electrons. The electrons can move around too. So here we have the positive charge of the battery, the positive side of the battery, connected to these positively charged holes, and it's going to push them that way, isn't it? It's going to repel them. What it really does is it literally slams them up against the PN junction. Over here, here's the negative side of the battery connected through the lamp to these electrons. Negative battery, negative electrons. Same thing. It's going to repel. And the same thing happens. It pushes the electrons up against the PN junction here. Well, in this case, what happens is the pressure from the battery literally forces the electrons into those holes. Remember, voltage is pressure. The pressure, the voltage from the battery, literally shoves the electrons into the holes. What it does is, because we've got electrons on this side pushing against the PN junction and holes on that side pushing on the PN junction goes away. Now, it doesn't destroy itself. It isn't like instantly gone or anything. As soon as I remove the power, that PN junction will pop right back up again. But essentially, it's just like pushes it aside. There's so much pressure there. It's like, you know, if I close this door here and I try to hold it, if one person's pushing on the, well, if there was a door, if one person's pushing on the door, I could probably hold it. But if I've got enough people pushing on the door, you're going to push through. Same thing here. If there's enough pressure, enough voltage, and it doesn't take very much, the electrons in the holes pushing on that door, on that PN junction, literally knock it aside, and the diode starts to conduct. Well, I don't think that part's that interesting. Okay, it does that. Great, wonderful. But what I think is interesting is the other way around. Let me put this back together again. Here's the positive charges. Remember, that's the type P silicon. The PN junction. Here's the electrons in the type N silicon. Let's turn the battery around. If I turn the battery around, is this thing conducting or not?
No.
Negativo, not. Okay. This is pretty cool. Remember, opposite charges attract each other. Here's the negative side of the battery connected to the positive charges. It's going to suck them this way, isn't it? Away from the PN junction. Positive, positive. Away from the PN junction. Here's the positive side of the battery connected to the electrons. Same thing. It's going to suck them away from the PN junction. Well, now not only do we not have the electrons in the holes pushing together at the PN junction, but we're left with an area here and an area here that's made out of pure silicon. What do we know about silicon? Doesn't conduct. It's an insulator. That's why it doesn't conduct the other direction. That's why these things are called semiconductors. They're called semiconductors because sometimes they conduct. They sometimes conduct. Sometimes conduct. Semiconductors. They're not called semiconductors because, oh, well, they kind of conduct, but they do a real shitty job of it. You know, but that's how it was explained to me at one time. It's like, well, you know, they kind of conduct, but they really don't do that good a job. Well, that's nonsense. Look. This thing is on. It's on. This light bulb is definitely on. There's no question about it. and yet when I reverse the diode, it's completely off. It's completely off or it's completely on. One or the other. So it isn't like it does a lousy job of conducting. When it's conducting, it's doing a great job. So that's why these things are called semiconductors, because they sometimes conduct. Does that make sense so far?